Okay, let's get started. Make sure you have the AWS access, but even if you don't, it's fine. You can always try it out later. So for this session, this is a lab session. So if you go to the tutorial website and I'll show. Go to the tutorial website and scroll down to the schedule. And the last item on the schedule is a lab session. So if you click on the lab hands-on with RL for computer arc security, so this lab will be loosely based on the content that Wenjie just presents. Let's get started. So if you click on that, this leads you to the RL4CAS tutorials lab. And so the lab is divided. Any questions? I'll help you later. So we will have a dedicated time for the I will walk around, and if you have login issues, I can help you at that time. So right now we're going to just talk about look at the code. We are not going to run the code yet. So part one, we introduce is how to write a reinforcement learning environment based on the GIM interface. And part two, once we have the GIM interface, we want to train the GIM environment and train an RL agent using some RL frameworks, such as TorchRL. And we are going to use TorchRL in this example. And part three will be the actual hands-on session in which you will be able to launch the RL training session and try to explore different architecture attacks. And part four is a little bit strategies. So basically, you modify the RL environment a little bit to incorporate some new actions in the RL environment. So let's get started with part one. So just to recap, we previously and for those of you who wasn't here in Wenjie's talk, so this talk is this lab is about using reinforcement learning to find the cache timing attacks in microprocessors. So traditionally, people use human experts to look at how the computer processor is designed and try to find out those cache timing leakage, cache timing attacks by humans. But in this work, what we are trying to do here is that we're basically trying to formulate the cache timing attack as a reinforcement learning problems. So basically, we are formulating it as a reinforcement learning game. And so in order to do that, we have to implement a reinforcement learning environment. And there is standardized reinforcement learning environment interface, which is called the GIM environment, which is the one we will be using in this example. So what we are going to do here is that we have a GIM interface, and what we want to do here is that we want to formulate our cache timing attack problems as into the GIM environment, so that we can use RL agent to automatically explore those cache timing attacks. So let's talk about the GIM environment first. So GIM environment, as you can see, is a standard interface developed by OpenAI, which also develops ChatGPT and all the famous stuff. And so basically, it is defined as a Python class with three methods. And so in this class, you need to define step function, initialization function, and reset function. And you can refer to the GIM official document, which I listed the link here. So basically, you can click on to here. So they have a more detailed document on like how the GIM works. But for our tutorial purpose, I will just explain the basic details. So GIM interface, you have to define the init function. So in the init function, you need to define the observation space and the action space of this RL problems. And second, you need to define the step function. And the step function, so basically in RL, you do the environment and the agent interact step by step. So in each step, you take an action, and then the state of the environment changes, and you get some reward, and you also get information whether this training episode is over or not by this down signal. And if you want to incorporate some additional information, you can put them in the info. And there is a reset function. So basically, after you done one episode of training, you want to reset the environment to a new state. So that's the three basic function GIM API that you need to implement if you want to formulate any problem as a reinforcement learning problems. And for our purpose, we are basically using the GIM environment to explore the cache timing attack. So to explore the cache timing attack, first of all, we need a cache. We need a proper way to simulate the cache. And so for this purpose, we provide a cache simulator interface. And so many of us are computer architects. So we are all familiar with architecture simulators. And so in this cache simulator interface, we provided with many basic functions that you can simulate. So for example, if you want to simulate a cache, so a cache can read, cache can write, you can flush a cache line, and you can parse an address into like different tags, offsets, and index. So these are the interfaces that we provide in the cache interface, and you can click on those links, which will point to the actual location where those functions are implemented in the code. So that's the cache interface. So we have two interfaces here. First, we have the GIM environment, and second, we have the cache interface. So in order to formulate the cache timing attack problem as a reinforcement learning problems, so basically we need to implement the GIM environment. So GIM environment currently is an interface, and we want to implement it using this cache simulator. So that's what we are going to do in this example. So as mentioned before, we want to use reinforcement learning to play the cache casing game. And Wenjie explained previously before that in order to play the cache casing game, we have to define the several things. First, we have the agent. Agent is the attacker, and the environment. The environment is a cache, which we provide the cache simulator interface to use. And there are different actions, like for the attackers. So the attacker can access a specific address and measure the latency. The attacker can wait for the victim to access a secret address, and the attacker can guess the secret. And we have some observations. So basically the observations is the latency of the attacker access. And we play this game in order to let the attacker guess the secret correctly. So every time when the attacker guesses the secret correctly, we want to give a positive reward to the attacker. And if the guess is wrong, we want to give a negative reward to it. And for each step, we are giving a small negative reward. And so for the reinforcement learning, it basically maximizes the long-term reward. So if we set the correct guess correct reward as a positive reward and guess wrong reward as a negative reward, and if we maximize this long-term reward, what we'll find is that we will find the attacker with more correct guesses and fewer wrong guesses and a fewer number of steps. So that's at high level how the cash guessing game works. And what we are going to do here is that we are going to implement this cash guessing game described in English into code using the gym environment. So in the gym environment, as mentioned before, to implement this, we need to define the actions, the state of the observations, and the rewards. So the action, in order to define the actions, you first need to define the action space, and then you need to define the concrete actions. So the actions are inside those action space. So the action space is defined in the init function of the gym, and the action is defined in the step function in the gym. So you can look at this document by yourself. So there is a hyperlink which links to the specific position of the code on how those observation space, action space is defined, and you can find them in the code. And so let's so we've also documented how those actions are actually defined in this document. So if you define actions, though there are, for example, when you read an address, and if there are n different addresses, then there are n actions corresponds to reading each address. And for victim access, there is one action. And for guess the secret, if there are m possible secret, then it corresponds to m different actions. And all in all, there are m plus 1 plus m actions. And then you can define the action space here in this way. So the action space is defined as a space dot discrete. The size of the action space is the length of the attacker address space, which is n, and 1 is represents the victim access, and there are m actions correspond to m victims possible addresses. So the action space is m plus 1 plus m. So that's how we define the action space, and once you define the action space, you also want to define what each encoding of action inside this action space represents a concrete action. For example, what action 1 represents, what action 2 or what action 5 represents, whether they represent, say, read an address, and if it represents read an address, what address does it represent? Or if it represents guess a secret, then what secret does it guess? So we need to translate this action encodings into the concrete actions. So that's why we define a parse action function, which parses action encoding into several different flags, including what the address is, whether it is a guess action, whether it is a victim access, whether it is a flush action, and whether it is what the victim address it is, if it's a guess victim access. So the body of this function is shown here in this link. So you can click on that to examine how it is implemented. Once we parse actions, what we get is this several different flags, whether it's a guess, whether it's a victim, whether it's a flush. And then what we need to do is that we need to actually perform these actions in the cache simulators. For example, if it's an attacker access, how do we invoke the cache simulator to actually access that address? For example, if an attacker reads an address, so what we can do here is that the cache simulator is the object of cache simulator is RL1, and if you want the cache simulator to read the address, so you do RL1.read and followed by the address. So the code, the actual implementation is shown here. And so if there is a victim access, you can also do L1.read followed by the victim addresses. So by invoking L1.read, L1.read victim address, you can perform different actions in the cache simulators. And so that's how you define the actions here. And also you need to define the state of the cache simulator, state in the RGM environment. So which is also documented here. And we also define the reward function in the step function. So we provide the link to when it is a guess action, if the guess is correct, what reward should be assigned. If the guess is wrong, what reward should be assigned. And if it's not a guess action, if the length of the attack is within the limit, what reward should we give? And things like that. So after we define the actions, the state, and the reward. So basically putting everything together, we put everything in and implemented everything inside the gym environment. And so basically in the init function, we define all these stuff. And in the step function, we define this. And then in the reset function, we define the like how to reset cache simulator. So the entire code of this gym environment that is implemented for the cache guessing game is shown in here. In the cache guessing game.py. So if you click on it, so this shows the entire code. So basically you can see it implements the gym interface, and you define the init function, the step function, and the reset function. So you can read this is 400 lines of code, but you can read it offline to understand how this is implemented in a cache guessing game. So now we have the cache guessing game implemented gym environment. So the next step here we want to do here is to train the with this gym environment. We want to train the RL agent using some reinforcement learning framework. That's where we are going to part 2 of this talk, which is about training the RL agent. So Vincent will cover that part on how to train that using TorchRL. So,
okay, yeah, so now I will go through the script to train the reinforcement learning agent. So as the name of the file says, it's PPO. So we talked about PPO, if you remember, during the first talk. So PPO stands for Proximal Policy Optimization. Basically, it means that the proximal stands for the fact that what we're going to do is that we're going to interact with the environment with our current policy. So at the beginning, imagine that your policy is completely random. You know, it's a neural network, uninitialized. It just outputs random actions. You collect data from the environment, a bunch of data, like let's say 1,000 trajectories, you know, something like that. And then we're going to store that data and look at the rewards that we have and try to optimize our policy based on those rewards. Basically saying, okay, this seems to work, this seems to work a little bit less. Okay, and we're going to do that a bunch of time based on the data that we've just collected. But the thing is that you can imagine that if you look at this data and then you try to optimize your policy, the policy starts to diverge from its initial configuration, right? So what is happening is that you start to sort of extrapolate what your policy is going to do in the environment, and you don't really know that yet because what you have collected is data with a random policy. Okay, so it starts to become a little bit tricky at some point to extrapolate that right, you know, because you don't have that much data and you're really in an out of distribution setting. So what PPO does is that PPO introduces this penalty sort of going further from the initial configuration the policy. And so you don't really need to care about that. It's already taken care of by Torchild, but that's what PPO is really doing. So now we're going to see what the training loop looks like. So this is all the imports, and this is our training script. So we first set a logger. We use weight and biases, or just because it looks nicer probably than some others. We save the configuration in some predefined safe directory that we create. Then you extract the parameters from the configuration. So far, so good. Now there is the environment factory. So what you will very often see in reinforcement learning is this kind of make environment function. So it's either a factory or a constructor. You can call it how you want. Basically, what we do is we create a function rather than an object because it's easier to pass that function from one process to the other because we're going to do a collection using multiprocessing. And it's usually easier to pass a function that creates something rather than an instantiated object. We don't necessarily need to because it's basically just a simulator. We don't need to instantiate the simulator to pass it to other processes. That's the kind of the idea. Okay, so we have the geo environment we talked about just now with a configuration that is passed to it. And this is basically our simulator for the cache attacks. Then Torchild provides you with a gem wrapper. So basically it's something that will read this data and write the data also from and to the gem environment into TensorDict, as I talked during the Torchild talk. So basically, this gem wrapper it expects a TensorDict in, and it's going to output a TensorDict out when you call the step function. Then we transform that thing because we would like to do a couple of things. So the first thing we would like to do is to tell this environment, okay, every time you reach a done state, what you're going to do is that you're going to sum up all the rewards that we have seen so far in the trajectory. And the idea behind that is that the total reward by design should be 1 when we have accomplished the task. That's the total reward. It's not the per step reward. So we need to sum those rewards throughout the trajectory. The other thing is that we do a step counter just to know how long our trajectories are, just for logging purposes. So create an environment here and a dummy environment. The dummy environment is basically used to gather some metadata, like what is my action space, etc., etc., etc. All these kind of things. We have a get model function. We don't necessarily to go through that now, but basically you pass all the configuration that you need, and it's going to give you a train model. We create a replay buffer. This is plainly and simply how we create a replay buffer in Torchild. We say that we want a replay buffer that stores TensorDict, so it's a TensorDict replay buffer. We say the kind of storage we want. This is a lazy tensor storage. So basically what that means is that we expect that this storage is going to store tensors or TensorDict. It's lazy, so we don't tell it yet what the structure of the data is going to be, which is very useful because the first time it's going to see a batch of data, it's going to say, okay, now I know what my data looks like, and it's going to be instantiated like that. You could have a lazy memory mapped memory mapped storage that's also provided by Torchild, for instance, and this one would save the data on disk. We're not doing that now because there is not really the replay buffer is not that big. But if you have a replay buffer that is as big as several terabytes of data, you probably need to store that on disk. Okay, we see the sampler that we want a sampler without replacement, as I will show in the training loop. And yeah, okay. We have our train model, and our train model can be decomposed in various species. The first piece is the actor, so the thing that is going to play in the environment. But as we talked about again during the first talk, another thing that we very often have in RL is a value network. And so the value network is also contained in the train model. We just have to call get value. And actually the tricky bit here is that the value and the actor, they share a common backbone. So there is sort of a backbone that represents the observations in a latent space. And then there is an actor head and a value head. And so we can get our value head by calling train model.get value head. And we get that thing. We're going to need that value head and the actor because the value head is basically the only thing that differs from the actor. In between the value net and the actor, you have a lot of stuff that is actually shared. So later we're going to use those two things independently. So this is when you create our loss module. So our loss module is composed of the actor, and as I said, the value head. So we just pass those two things to our PPO loss module, and that's basically everything that we need to do with TorchRL to create a loss and be able to train our model. These are just some hyperparameters that we pass. GAE stands for Generalized Advantage Estimation. We talked about advantage before, so the advantage is basically the total reward that you got right now doing a certain action minus what you would have expected for the current state, So this gives you the advantage of taking that action compared to the other actions that you could have taken. And we have a module that is specialized in computing that thing. Mathematically, it's a little bit convoluted. It requires quite a lot of operations, so we have made sure that this was as vectorized as possible in TorchRL. And you see that here I pass the full value net, not just the value head. You see that's the reason why I split those two things. Right. Okay. We create an optimizer. We pass the parameters. Create a data collector. So the data collector, there are three types of them, but let me take the simplest one. So we create a data collector. We give it an environment. We give it the actor and some parameters. So basically, this object here is something we can iterate over and get batches of data that represents the actor playing in the environment for a certain number of steps. So this is the data that we're basically going to use to train our model. Right, let's go straight to the training loop. So we iterate over the data collector, we get batches of data. We record the number of frames that we have computed, and we do some modifications because we want also to mark the last state as done anyway. That's super important. You could even skip that. Right, this is the evaluation. I won't spend too much time explaining that. The training loop, okay. So we have the main training loop where we get data. Now we have a sub-training loop where we're going to iterate over that data several times to optimize our policy. Remember that in the meantime, what PPO is going to do is that it's going to add some sort of constraint, to make sure that our policy is not going too far apart from where it was when we collected the data. Okay, so we put our actor in train mode, and we do a certain number of epochs. In the configuration that we use 10 epochs. It could work with 5 or 20, something in that range. We compute the advantage each time we do an epoch with the updated version of the value network. And then we populate our replay buffer with that data. Okay, so the replay buffer we built before, it just contains one batch of data, the batch that we just collected. And then we're going to iterate over our replay buffer. So basically consuming the data one point at a time, or not really one point, but one sub batch of data at a time. And we just get those batches from the replay buffer. We pass those batches to the loss function, and we get a dictionary that represents the various losses, one loss for the actor and one loss for the critic. The reason we split those losses into TorchRL is just because sometimes research scientists, they like to do things differently and have one optimizer for the actor and one optimizer for the critic. So we prefer to split things, not sum them by default. Okay, but what we do here is just that we sum them actually. We do a backward pass, we do an optimization step, and then we zero the gradient, and that's basically it. So to recap, we have all the instantiation of everything, like the model, actor, critic, replay buffer, data collector, etc. And then once we have all of these things, we start collecting data through the data collector. Once we have this data, we do a certain number of epochs. At each epoch, we start by computing advantages. We take that data with the advantages, we put it in the replay buffer, we consume our replay buffer a certain number of times, so there are a certain number of epochs, and every time we sample something from the replay buffer, we compute a loss value, backpropagate, optimize the parameters, and go back again. Overall, if you, in terms of numbers, and then I will give you back the mic. In terms of numbers, the number of, we determine basically usually in RL how many frames, how many steps we're going to collect in the environment. That's sort of a measure of the computational budget that you allow yourself, So people will tell you, oh, I have solved that problem in 1 million frames or 1 million steps. It means that they tried 1 million times, you know, to look at the state, make an action, and then try to learn from that interaction. Typically here we use 1 million frames. If the problem is more complicated, usually you need more frames. If the problem is super simple, you might need less frames than that. We're usually in RL around the million frames. What else? Epochs, I told you we have about 10 epochs in the config. And we have pretty big batches of data. The sub batches that we build, they're like 512 elements. But the batches that we collect from the environment, each time we iterate over the data collector, they're, I think, in a config about 8,000 steps. So that kind of gives you the scale of everything. And the full training loop on an A100 GPU should take something like 50 minutes to 1 hour. And it should be solved at about 400,000 frames, which is about like 20-25 minutes, something like that. So that's about the time it takes.
Thanks to Vincent for the nice introduction about the training scripts using TorchRL. So with all that, we will actually run this script on the AWS to see what happens and how it trains. So to follow the document, you can go to the lab session and part three. So we'll introduce how we access the AWS environment and how we launch the training here and run that single training script. So I'm showing the terminal here. So maybe I think I'm going to split the screen half by half. So yeah. So let's first log into the AWS screen, in which if you have received the email, you should know how to access that. Let me find my access. So yeah, this is in IP. So the password is email here separately. So yeah, so now we are inside this AWS machine and G5X large instance, and it has a GPU. If you do NVIDIA SMI, you can see. Okay, sorry about that. Maybe let me merge this. Where is the document? Yeah, I see. Okay. So we basically go over this document, which is pretty fast since we already have a pre-built Docker image. So first thing what we want to do here is that we want to pull this Docker image from Docker Hub. So maybe I should enlarge this a little more. So basically do a pull Docker Hub from this Docker image, which was pulled before, so you won't wait too long. So after this is pulled from the environment, you want to launch this Docker image by using this. You see this, the running option has some dash GPUs, or which means you launch expose the GPU to the Docker instances as well. So now you are inside the Docker shell. And since we are running lots of Python scripts, so we want to use Conda environment to manage the Python script. So what we do here is that we want to activate the Conda environment inside the VM. So, and then activate this Conda environment. So this Conda environment the torch is already installed there, but the torch RL is not the latest version, so we are going to update the torch RL inside on this AWS server. So we do this by, so first we install the TensorDict, which is a dependency of torch RL. So this takes several, maybe 1 minute. So let's wait. So if you are accessing the server, can you follow in this? Or if you have any questions, please let me know. Yeah, it got stuck. Yeah, let's just wait. And in the meantime, we want to, yeah. So now the TensorDict is installed. We want to install the TorchIO, which is here, which is here. So we copy and paste this command. So this will install the latest nightly build version of TorchIO. And while we are waiting for the installing TorchIO, we can create a 1DB account simultaneously for visualizing the training progress. Because our TorchIO is integrated with 1DB to visualize the training reward and those statistics that. So to do that, basically we need to sign up for the 1DB. So we can click on this 1db.ai link. So this is signed out. This is already signed in, but let's do it another time. So this is a website of 1DB, so you can sign up using using Google or using your email. So I'll just type my email password as and then you can check your mailbox to verify that. Let me check my mailbox. So they are asking you to write the full name. And academic. Yeah, so now I've created my new 1DB account. So what we will do from 1DB here is that we want to get the credential from 1DB in order to connect to the TorchIO. So what we do here is that we click on the upper right and then click on the user settings, and we can scroll down. But by the way, all these instructions are also in the document. So if you cannot follow, you can also look at document. So here there is a danger zone API keys. So basically you copy these keys into clipboard, and then and then you can use it later when you launch the Torch RL training. So let's launch the Torch RL training now. So let's go. So it's part 3. Website. So yeah, you can also follow this document here on how to create the 1DB. So once you have the created a 1DB account, we can now clone the code and launch the training. So basically we can do the clone the code, git clone https RL4CAS Lab. So this clones the all the code base into the repo, and we go to the C lab SRC TorchRL directory. That's where all the TorchRL scripts are. And now finally we can launch the TorchRL training. So yeah, so then it asks you about the 1DB stuff. So whether you want to create a new 1DB account or use an existing account or don't visualize the results. So since we have already registered a 1DB, what we can do is that we can use an existing one. We enter 2 here, and we basically paste the API keys. Remember the API keys here, we copy and paste it here. So now it's connected to 1DB. So yeah, now it starts training, and it's printing out some statistics like the reward loss critics, and we can also open the 1DB to visualize all these results. So we go to the 1DB in on the web. So if we click on here, we can show the training that we just launched. So we click on this. So it will show like 12 charts. So the first page shows 6, and the second page also shows 6. So they're showing like test reward, episode reward, and train reward, and test episode reward. So what we are looking at here is that we want the test reward to be as high as possible. So if so remember when we when the guess is correct, we assign a positive reward, and when the guess is wrong, we assign a negative reward. So if you want all the guesses are correct, then the reward should be higher. So that's why we want the reward as high as possible. So we look at the test reward, test episode reward. The episode reward means the reward of the entire episode. So for example, if your trajectory takes 10 steps, and each step has some reward. So the test episode reward is the summation of all the step reward within that trajectory. So we are looking at this test reward. So basically it's training right now, and we'll take a look at how it looks like. And I'll pause here for a moment. So if you are able to see launch this training on your own, then that's nice. If not, if you have any troubles launching it, please let me know. So yeah, we are seeing the test reward is increasing and the training reward is also training episode reward, which is on the next page, is also increasing. And at the end of the day, we want the reward to be something around 1. So because we assign, if your guess is correct, we assign +1 reward, and if the guess is wrong, we assign -1 reward. And you can calculate the average reward considering like the correct rate. So if your guess is 100% correct, then your episode reward would be 100% times 1 plus -1, which is wrong guess reward times 0, so which is equal to 1. So the training still runs. So we will wait for several seconds to. I mean, it's expected to reach like reward +1 within like 10 or 20 minutes. So let's see how it runs. So and let me know if you have any issues launching this experiment. Rather than like we stare at this and wait for the experiments to run, I will step into the last section, part 4, which is kind of optional due to time reasons, but I think we can talk about it, and you can finish it offline. So the part 4 is about flash and reload cache timing attacks. So previously we have talked about how we actually implement the GME environment using the cache simulators. But the problem is that for that environment, we didn't include the flash actions. And but there are many cache timing attacks that requires a flash action. So what we want to do here is that we want to incorporate the flash instruction into the GME environment as well. So originally the GME environment we implement didn't have the flash instruction. So now we want to incorporate that. So in order to achieve that, what we need to do here is that because we are adding more actions, so the action space increases. So first of all, we want to extend the action space. So if we would look at the original action space, the code is the size is the size of the action address space +1 plus the victim address space. But if we want to incorporate the flash instructions, we need some more additional encoding space to represent the flash action. So that's why we extended the size by 2. So basically, the size is now 2 times the attacker address space +1 plus the victim address space. So that's how we increase the action space here in the code. And second, we need to modify the action parser. So even if we increase the space, we still need to basically encode those new actions that we want to add. So basically, we need to implement that in the parse action function. So this is defined somewhere here in the parse action function. So in the parse action function, there are 2 cases. First, if we don't incorporate the flash instruction, we will parse the action in this way from line 404 to line 440. But if we want to incorporate the flash action, we want some additional encodings. So we have 4 different scenarios. which corresponds to like attacker access, flash, victim access, and guess. So that's how we modify the parse action function. And last, we need to perform actual flash inside the step function in the cache using the cache simulator. So remember the cache simulator API which was defined in the part 1. Cache simulator API, we defined a read, write, flash, parse address, and the initialization. So basically, we want to invoke the CL flash function in the cache simulator in order to actually perform the flash inside the cache simulator. So that's where we need to modify in the third part to perform the flash instruction in the step function of the GIM environment. So basically, the step function is here, and what we need to do here is let's see. So basically, we want to perform the flash action here. So basically, we will need to do some. So we can look at for example, line 283, which performs the read action. So what it does is that self.l1.read followed by the address and the current step. So what we want to do here is that we want to do the similar thing, but perform a flash instruction instead. So what we can do here is that we can use this line, but change this read to CL flash. So that's how we perform the flash instructions here. And after we fill in that line, we can launch the training environment to train a new agent that incorporates the flash action into the environment, so that we can find new attacks that like flash and reload type of attacks. So that's for the part 4. So you can look at the document in detail in offline in order to perform the part 4. But let's go back to the part 3 to see what the result looks like now. So the testing reward is still not there yet, but you can monitor the reward. So once its success, the test reward will reach some value around 1.0. So basically, at the end of the day, we will get a RL model that can perform those cache timing attacks, and we can sample those trajectories using the let's see. So once we have let's see, sorry. So assume that we have finished the training. What we want to do here is that we want to find the trajectory, which we will provide a script in part 2. So basically, in part 2, we want to sample in the policy net to get the attack trajectory using TorchRL. So the script will look something like Python sampling trajectories, and you specify the saved path and the number of rollouts where you can sample in those attacks. And so that's that. Any questions, or are you able to get like very high 1.0 reward for the test episode reward? It sometimes it takes a while because reinforcement learning is known for its instability. So depending on like what the random seed you choose, the result can vary significantly. So sometimes it takes slightly longer time.